Welcome back to Chem Crash. Today in our second pre-organic chemistry lecture, we're going to be discussing the valence bond theory and are applying our knowledge about atomic orbitals that we learned from last lesson. What we know so far about covalent bonding is through the Lewis theory. So we know the three key points about what a covalent bond is. We know that they're a shared pair of valence electrons between nonmetals. So how we see it with the Lewis diagram is something like this. If we were trying to represent the bonding between the diatomic fluorine molecule, so F2, then we would show it as follows. Drawing the second F here. So we can clearly see that these two electrons are being shared between these two fluorine molecules. This is how we would previously represent covalent bonding. However, now with our knowledge that electrons don't only act as particles, but they also act as waves, along with our knowledge about atomic orbitals, we represent bonds a little bit differently, and we represent it through the valence bond theory. So the crux of the valence bond theory is essentially represented in this diagram right here, where we have two hydrogen atoms, and each of them have their atomic orbitals. In this case, we know that the electron configuration for hydrogen is 1s, so we know that both of these are s orbitals. We can see that as you go down, the orbitals overlap until they form a new orbital, which we call the bonding orbital. Bonding orbital. So essentially, the definition of the valence bond theory, roughly, is the overlap of half-filled atomic orbitals to create bonding orbitals. This new bonding orbital that we see down here becomes the new most probable region of finding the shared electrons in the new bond. So we know before from our atomic orbital lesson that this region, represented by the circle, and we know that this shape is the s orbital, is the region where it's most probable to find the electrons for the hydrogen atoms. But when they form a bond, those orbitals, those atomic orbitals, overlap until you form the new bonding orbital. And this new orbital is where it is the most probable to find both electrons that are being shared by the hydrogen atoms. We also know that energy is released when a bond is formed. So, we then also know that this form, this bonding orbital I'm going to represent as BO, is more stable. Another key thing to note about forming bonding orbitals is that there is an ideal bond distance for each unique pairing that maximizes the attraction and minimizes the repulsion. So when we have two orbitals, this would be too far away for there to be an overlap, and this is too far away for them to form a new bonding orbital. There isn't enough attraction. If they're too close together, if there's too much overlap, then the electrons start to repel each other, and there's repulsion. So this is lack of attraction, and this is too much repulsion. Sorry, not enough space there. Too much repulsion. So if we get them at the perfect distance, which is sort of represented by this here, then it's able to form the bonding orbital. Now we're going to look at a couple of examples to discuss what kind of bonds are formed when different types of atomic orbitals overlap with each other. So the first example we're going to look at is the HH covalent sigma bond. So the sigma bond is the type of bond that we're going to be discussing through the HH bond. So specifically, it's the SS sigma bond as written down here and here. So we know that hydrogens, with its electron configuration of 1s, only has the s atomic orbital. S atomic orbital. So when two hydrogen atoms bond with each other, we have two s orbitals overlapping. This type of overlap is known as head-to-head overlap. It will become clear the difference or what makes it a head-to-head overlap as we go through the different types of overlapping. But for now, just know that when two s orbitals overlap, it's always going to be a head-to-head overlap. Now, a head-to-head overlap means that it's a sigma bond. So therefore, it's a sigma bond. What characterizes a sigma bond is that it is cylindrically symmetrical around the bond axis. What the bond axis is if we have a hydrogen atom and another hydrogen atom, this hydrogen atom is bonding this way with this hydrogen atom. And this hydrogen atom is bonding this way with the first hydrogen atom. So we can see that they're bonding across this axis here, which we call the bond axis. So when the sigma bond forms, it creates a cylindrically symmetrical shape around the bond axis, and that's what characterizes a sigma bond. Let's look at a second example of another type of sigma bond. So this sigma bond is a PP sigma bond, specifically a PZ-PZ sigma bond. We know that s orbitals from the last example are spherically symmetrical, which means that they have no orientation, which means that there's only one configuration. But with p orbitals, we know that they aren't spherically symmetrical, as we talked about in the last lesson. So they can have three configurations: px, py, and pz. This means that when they overlap with each other, they overlap in different ways. So if we have electrons in the p orbital, which fluorine does based on its electron configuration, then the p orbitals will overlap in order to form the new bonding orbital. Specifically, when the pz orbitals overlap with each other, in this way, then we get another head-to-head overlap, which means that this is again a sigma bond, and specifically a PZ sigma bond, because the PZ from the first fluorine molecule is bonding with the PZ from the second fluorine molecule. And again, this has all the characteristics of a sigma bond. It's cylindrically symmetrical across the bond axis, which we know is right here. So what we see is a similarity between the HH sigma bond and the FF sigma bond is that even though they're from different orbitals, we know that they're single bonds. Where we get into different types of bonding orbitals is when we get into double bonds, as we see here in this example with the diatomic oxygen molecule. So the diatomic oxygen molecule has a double bond right here. So this double bond makes it so we have two orbitals overlapping with each other. This means that the pi orbitals, which overlap with each other, have to overlap in different configurations. So the first overlap that we see is the example we looked at last time, which is the PZ-PZ sigma bond, because they're overlapping in a head-to-head overlap like this, where they overlap right here. But we need a second orbital overlap. So now we have a py-py pi bond. So this overlap is different. This overlap, we have a pi bond like this on the y-axis. And we have the other pi bond from the other fluorine molecule like this also on the y-axis. They can't overlap head-to-head like we did with the two pz orbitals. These are py. So the only way they can overlap when they approach each other is side to side. And so we get an overlap that looks like this, where we have our first pi orbital, and then we have our second pi orbital, and it overlaps specifically in these places. You can see that there is an area in the middle here, because we know that pi orbitals, or p orbitals, have nodes where they don't overlap at all. And they overlap on the top and on the bottom. So essentially we can write here that a side-to-side overlap creates a pi bond. And what characterizes a pi bond is that they're not cylindrically symmetrical, and they're both above and below bond axis. Okay, so that's what characterizes a pi bond. And we get pi bonds when we introduce a double bond. Now moving on to our final example of the nitrogen molecule. So the nitrogen molecule has a triple bond. We know that a nitrogen molecule looks like this. That means that all three pi orbitals are overlapping with each other. We have the PZ-PZ sigma bond from the head-to-head overlap that we saw before. We have the PY-PY pi bond from the side-to-side overlap as we saw before. They're not overlapping. Just like that. And now we introduce the PX-PX also pi bond. So the PX orbital is hard to represent in a drawing, but the px orbital is sideways like this. So that means that they are not facing head to head with each other, so they again are going to overlap side to side exactly the same way as the py. And therefore it also creates a pi bond on either side of the bond axis. So now we get three different bonding orbitals that look like this, where we have a sigma bond in the middle and two pi bonds encircling the sigma bond on all sides of the bond axis. That is essentially the valence bond theory in a very basic form in a nutshell. But the valence bond theory doesn't take into account orbital phases or the second law of thermodynamics. So we see what we do to deal with that in the next video. Thanks for watching.